And finally, we have Derek Nelson with PipelineDB.
Hello, everybody. My name's Derek Nelson, and I'm going to talk to you for a few minutes about PipelineDB, in particular, why you all should care about that here at the In-Memory Computing Conference. So at the highest level, PipelineDB is a relational database. One of the most unique things about it, though, that makes it different is that it's actually built to run SQL queries continuously on streaming data that's being flowed into the system. And incrementally updating the continuous query results in real time, which are backed by tables in the underlying storage engine. And so ultimately, it integrates streaming computation and relational storage on the same exact hardware. So in order to achieve this, we've added a few primitives that you guys probably haven't heard of before with the typical legacy SQL database. And the first one that's sort of front and center with our system is what we call the continuous view. And a continuous view can be thought of essentially as a very high throughput, incrementally updated, materialized view. So as you know, the canonical example of what a continuous view might be is select count star from stream. You could stream trillions of events through this continuous view, and the only thing that's stored in the database is this count that's just incrementally updating as new data flows through the system. So that's the most important primitive that we've added. That's a little bit different. The second one is the continuous transform, and a continuous transform reads from some stream, applies some sort of operation on each data point in that stream, and then does something with that event that it produces, whether it writes it to a new stream, writes it out to Kafka, writes it out to some other external data store. It could be potentially anything. And finally is the continuous trigger. And a continuous trigger is a lot like a regular SQL trigger. It's applied to a continuous view and gets fired anytime something interesting happens. So you can really chain these things together to create arbitrarily complex streaming SQL topologies. But before we get into like an example of what one of those looks like, I wanted to talk about the motivation behind us building this product in the first place. And the first thing to think about is, people ask me all the time, why is there so much fragmentation in the data space, particularly with databases? And it all really boils down to the fact that data processing needs are vastly outpacing hardware innovation, and in particular, disks. So storing data, critical data, in main memory is an obvious workaround to the disk bottleneck that's pretty convenient and works in a lot of cases. But what we found in our experience is that for a vast set of use cases, not 100% of them, but probably 80 or 90% of them, we can actually do a lot better than just putting stuff in memory for performance, if we rethink how we kind of process these workloads. So this came from three critical observations. And the first one is that if you ever need really, really fast query results, then it's almost always the case that you know the query that's producing that result in advance. There aren't human beings inventing new ad hoc queries 1,000 times a second when they need responses right away. So this is particularly true if the consumers of your database are other applications. They're by definition pre-programmed. And so this is the observation that's really the crux of the whole system design. And so the second thing is, if we know the queries in advance, then we can very, very efficiently compute the answers to those queries incrementally in real time. And the third thing is, if we can do that, if we can compute answers incrementally in real time from streams, then we actually don't need to store any granular data at all. We just need to store the answers. And so to give you an example of what this looks like, a traditional database, you will accumulate some amount of data, whether it's in memory or on disk. So you store it first, and then you can query it after that. You define the query, run the query, looks over the data that you've stored, and you get, some result back. And so the continuous query actually inverts that model. And in that sense, we like to think of it as PipelineDB as an inverted database. So we actually query data and then store it. And what that looks like is something like this. So the answer is always up to date, and it's just incrementally updating as data is flowing in to the system. And that's the only thing that's stored right there is the number. And so to give you an example, and going back to the primitives that define our system, to give you an example of what that actually looks like is, here's an actual topology that you might see. So a lot of people are reading data from Kafka. PipelineDB integrates natively with Kafka. So you might apply some continuous transform on a Kafka stream. In this case, we're joining Kafka data on some static table stored in the system. And then we're writing that result out to another stream, which this continuous view is reading from. It's a simple average grouped on some column here. And we can also attach a continuous trigger to that continuous view that sends a HTTP post request when the average here crosses some boundary. In this case, it's 10. And also, if any standard SQL client wants to read from this continuous view, they can do that at any time by just running a select query on it as if it were a regular table. And any result they get is whatever is most up to date in the system at that particular point in time. So to wrap up, the benefits of this model, first and foremost, is you can achieve streaming analytics with only SQL. There's no application code required, which is a pretty new thing. And this results in extremely low engineering overhead. And you can also deploy new continuous queries with no downtime. You don't have to deploy new application code onto the topology. You just write a new continuous view, and everything starts working. And another main benefit is the continuous query model enables very sustainable and cheap infrastructure. So fundamentally, what this query first and then store model does is it breaks the dependence between database size and complexity. In other words, consumed resources, memory, disk, whatever. It breaks the dependence between that and the total amount of data that you've actually ingested. So here, the green line represents the database size over time. The red line represents total data that database has actually ingested. Another benefit is that real-time push becomes possible without polling. Because all of our query results are updated incrementally in real time, we actually know the instant something interesting happens, and we can do something, in this case, again, making an HTTP post request when that thing happens, the instant it happens without any sort of polling or stuff like that. And finally, because it's a SQL database, our system works with all standard SQL clients that are already out there. By design, we actually don't even have our own libraries, so it works with pretty much every single programming language in existence right now with very little engineering overhead. So thank you. Come find us at our booth if you guys want to know more.